All right, so in this video, we're going to cover covariance stationarity. So this should be review since we covered it last semester. It's already in the notes. So a covariance stationary process. Let's say we have a stochastic process xt, and xt is going to be covariance stationarity. So covariance stationary if the expected value, so if it has a constant mean, so if the expected value is going to be mu, so it's the same mean throughout time. So it's covariance stationary if it has a constant mean, if it has a constant variance, so if the variance is constant throughout time, and if it has a constant autocovariances, which would mean the covariance between, say, xt and some lag k is equal to some number. And this is for all k equal to or greater than 1. So as a constant autocovariances. So this means that autocovariances depend only on k. The lags, it only depends on the number of lags and not on time. So it doesn't change over time. So if it's k, if for the model, or if for xt, it depends on 5 lags, then it should depend on 5 lags throughout the entire process. It shouldn't change over time. If it did, then it's no longer covariance stationary. And for covariance stationary, it only focuses on the first 2 moments. So the mean is, of course, the first moment, and the variance is a function of the second moment. So covariance stationarity only focuses on the first 2 moments. The mean and the variance are constant across time, and the covariance between xt or x and x with some lag depends only on the distance between the 2 terms. It depends only on the lag and not on the location. So it doesn't depend on t. So this would mean that the correlation between x at time t and x with k many lags depends only on k. So it depends only on k and not on t. So this is covariance stationarity. So now let's talk about weakly dependent time series. So weakly dependent time series is a stationary time series if it's almost independent. So for a weakly dependent time series, so it's weakly dependent time series. So weakly dependent time series if it's almost dependent. So as k, or almost independent. So as k gets large, the correlation between our x and x with some number of lags is going to go to 0. So covariance stationary time series is weakly dependent if the correlation between x and x with some lag goes to 0 quickly as the number of lags gets large. So k many lags, as k gets large, the correlation between x and x minus k many lags is going to go to 0. So as they get further apart, the correlation gets smaller. So a covariance stationary process, So a covariance stationary process is considered asymptotically uncorrelated if the correlation between these two goes to 0. That's beyond the scope or it's not really beyond the scope of this class, but the proof behind it is it's not important for this class, at least not important at this time. There's no proofs in this class. So if a process is weakly dependent, then it replaces the assumption. So one of the really important things of this, if a process is weakly dependent, then it replaces the assumption of random sampling. So if this is true, then the theories behind, or the central limit theorem, still holds. So it replaces the assumption of random sampling. So if this holds and is weakly dependent, and it implies that central limit theorem still holds. Because it implies that central limit theorem still holds, we can use ordinary least squares. So if this is true, if it is weakly dependent, and it implies central limit theorem still holds and it replaces the assumption of random sampling, then you can use ordinary least squares, OLS, to find the coefficients. So if a time series is weakly dependent, then you can use ordinary least squares to find the coefficients. So that makes it a lot simpler. If it's not weakly dependent, then you cannot use ordinary least squares to find the coefficients. So this is so we talked about covariance stationarity. We talked about a weakly dependent time series. Let's do an example. Let's do an example of what this could be. So the simplest example of a weakly dependent time series is an IID random process. So let's do a ZT, where T equal to 1, 2, and so on, or it starts at 0, goes 1, 2, and so on. And it's an IID sequence, so it's independent and identically distributed sequence. It's an independently and identically distributed sequence where the expected value of ZT is going to be equal to, it's going to have a constant mean. And let's say the variance of ZT is a constant variance. Let's say the covariance between ZT, so Z, the current period, and Z for any K, is equal to 0. And this is equal to 0 for all K. And this is K equal to or greater than 1, because if it was 0, then of course the correlation would be 1. It'd be perfect, perfectly correlating, because it'd be the same thing. So this would be an example of a weakly dependent time series. It's a very very basic weakly dependent time series, but it still works. So this would mean that it would be ZT be equal to the mean plus and some noise. If we talked about this last semester towards the end of chapter 10, or towards the end of what we had, if the expected value of ZT is equal to 0, then that would mean that this is a purely random process. Then purely random. Purely random. It may also be called a zero mean white noise process. So if that were the case, if the mean of ZT is 0 and there are no covariances, constant variance, then ZT would just be equal to the residual, or to the error term. So this sums up covariance stationarity. In the next video, we'll cover a moving average process, and we'll review that.